Hi, welcome to video 2.3e, higher order derivatives. This is very, very easy. So basically, at this point, we've been talking about the derivative, which is really called the first derivative. And these are the different notations, of course, that we've been using. So what you can do is you can take the derivative of the derivative, and that is known as the second derivative. And this is the common notation, the double quotes. Instead of dy dx, you'll put d squared y over dx squared, and here you'll just put a square. Now the reason it looks the way it does right here is really the way you can think of it. Dy dx is really the derivative with respect to x of y. So here you're taking the derivative with respect to x of the first derivative, which is dy dx. You can kind of naturally see there's two d's here and two dx's there, so that's why the notation looks the way it does. Third derivative, of course, would look like this, etc. Fourth derivative, sometimes they'll use Roman numerals, sometimes they'll just use a regular number. Please be aware of the fact that the fourth derivative at x does not mean f of x to the power of 4. That's not at all what it means. Okay, so here's some examples. They're going to give you f of x and ask you to find the second derivative. So here's your original one. Now, of course, I could use the quotient rule, but that's way too much work. If you notice this is the denominator of a monomial, you can split it up. So again, that idea of simplifying f of x before you take the derivative. Now I'm going to take the derivative. I'm going to have 1 plus 0 plus 1 times x to the negative 2, which is 1 plus x to the negative 2. Notice I'm going to leave it with the negative exponent because I'm about to take the derivative again. The second derivative is going to be 0 and then minus 2 times x to the negative 3, which is a fine answer. Of course, in multiple choice, they'll probably write it with positive exponents. 101 to 102, they're giving you the second derivative and asking you to find the third. So you're really only doing the differentiation process once. But again, learn to rewrite. You could do a quotient rule on 2 over x. It's just going to be much easier to call this 2 times x to the negative 1. And then you don't have to do a quotient rule. And of course, the derivative is 1 plus 2 times x to the negative 2. That's the answer with a negative exponent. There it is with a positive exponent. And there it is with as a single fraction with positive exponents. And that would probably be the multiple choice answer. Here, find the first derivative at 2, given g of 2 is 3, g prime of 2 is negative 2, h of 2 is negative 1, h prime of 2 is 4. This really doesn't have anything to do with second derivatives, but we're getting towards the end of 2.3 here. So they're not giving you f of x or g of x or h of x. These are unknown functions. All they're giving you is this information right here. So they're giving you that f of x for number 106, f of x is 4 minus h of x. We want f prime of 2, so we'll start by finding f prime of x. The derivative of 4 is 0. The derivative of h of x is h prime of x. Then we replace all of the x's by 2. And now you go back up here and see, oh, h prime of 2 is 4, and therefore the answer is negative 4. So very easy. Here, f of x equals g of x times h of x, so it's the same thing, same given information. This is number 108, so same given information. So here we're going to do a product rule. So we do our product rule to find f prime of x, and then we replace all the h's by 2, and then go back to the previous page, and you'll see they've given you all these numerical values. And number 112, let me have you have a look at what we're looking at here for number 112. Okay, so what it says on number 112 is the graphs of f prime and f double prime are shown on the same set of coordinate axes. Identify each graph. So the question is, which one of these is f of x, which one of these is f prime of x, which one of these is the second derivative. Now you'll notice you have a parabola, you have a line, and you have a horizontal line. Now if you think of the degree of a parabola is ax squared plus bx plus c. It's a quadratic polynomial. The degree of a line, of course, is 1, and the degree of y equals 0 is 0. So if you think about it, the derivative of something to the power of 2, when you subtract 1 from the exponent, will become something to the power of 1. And for example, if this is y equals, I don't know, x plus whatever, the derivative of that would be, I guess this is y equals 2x plus something, the derivative would just be 2. So your f of x is going to be your quadratic, your f prime of x is going to be your linear, and your second derivative is just going to be a constant. 127 to 130, it looks very intimidating. It is not, okay? They're introducing the concept here all of a sudden of a differential equation. Now, all that a differential equation is an equation that involves derivatives, first and or second and or third derivatives. So you'll notice each of these is an equation, and in each case they have a first derivative, a second derivative, a third derivative, a second derivative, a first derivative. Each one of them has at least a first derivative in it, or maybe a second or a third derivative in it. But they're not asking you to solve these differential equations, which is very difficult to do. What they're asking you to do is verify that the function that they're giving you over here satisfies the differential equation. So, for example, number 128, you're given this function and you're asked to verify that this function satisfies this differential equation. So basically what we're going to do is take our function. You'll notice there's a y prime, a y double prime, and a y triple prime. So I'm simply going to find y prime, y double prime, y triple prime. When I've got those expressions, I'm going to plug them into here and show that indeed the left side equals the right side. So the first derivative is 6x squared minus 6. The second derivative, therefore, is 12x. And the third derivative is, therefore, 12. So I plug that in. It's just substitution. And when I finish substituting and I multiply through, get rid of the parentheses, and I simplify, surprise, surprise, same thing, both sides. So, on the TI, the way to do the different derivatives, first, second, and third derivative, is in the template, you're going to access this key. So let me show you that. So when you access here, you'll notice there's one for derivative, this is one for the second derivative, and this is one for any derivative you want. So when it pops up, you have to tell it with respect to which variable, ddx, ddt, and then you'll enter your actual function right there. So, for example, the second derivative of the function 6x to the fifth will give you an answer of 120x cubed. If you want the fifth derivative of 36x to the 78th, attractive. And if you want the fifth derivative of 36 times x to the 78 evaluated at x equals 368, I don't know why I don't have the answer here, but it should be there. And that's the end of video 2.3e.